Très bien. Bon, bonjour à tous et toutes. Bonjour à Giuseppe, bien sûr. Donc, Giuseppe, Parasiliti, Anton. Votre email, il y a toujours marqué Giuseppe Parasiliti. J'apprends que c'est Parasiliti Anton. Donc, le jury, que je vais présenter, est là pour vous écouter, présenter donc vos travaux de thèse que vous avez réalisés. Donc je présente. Voilà, le jury est sous nos yeux. Ah bah, c'est super. Très bien. Donc Olivier Vauquelin vient de c'est Marseille. Emmanuel Audus de l'Université Paris 13. Catherine Weissmann de d'Alembert, de ce laboratoire. Vous me déprez, je suis quand même à Sorbonne Université, du laboratoire LJLL. Et les superviseurs qui ont encadré votre travail, Thierry Lagré de ce laboratoire, Nora Aïsoued de Summit, qui est centré à Sorbonne, Johan Penel de l'INRIA, LJLL Sorbonne également, et Marguerite Dols, qui est de gaz et transport et technique gaz, là où aussi c'est vous qui avez donné le travail, voilà, qui avez proposé au thésard et aussi donné les moyens de préparer ce travail. Très bien. Donc vous faites votre présentation, comme d'habitude, 45-50 minutes, donc il sera en anglais, parce que vous trouvez ça plus agréable, c'est très bien. Et puis, mais en revanche, les questions pourront être données en français. Et nous vous donnons donc la parole. Merci.
Merci. I am Giuseppe Antone, and I will show you the work I have done on the modeling of gas flows in pipeline networks during my 3 years of PhD. During my thesis, I was helped by the laboratory LJLL, the Institute d'Alembert, and the service unit Summit, which make links with between university and industrial needs. And we have an industrial help that is from the firm Gas Transport Technique Gas. GTT has orders for 1.5 billion and has two-thirds of the LNG carriers in the world. It conceives technologies for the maritime transportation of liquefied natural gas. And during the transportation, there are many scientific issues that arise in the tanks where the natural gas is put, and sometimes prototypes are not feasible, and modeling and numerical simulation are necessary to understand the behavior of the gas. In particular, what we have done is to study the isolating gas that separates the tank from the exterior, and that allows to maintain control of the behavior of the natural gas. As you can see here, you have the gas that normally is nitrogen or helium that is inside a pipeline network that you can see from the inside of the tank. There are two key features in this problem. One is the difference of temperature from the interior and the exterior, that is little I. We go from around 100 at the interior to almost 300 at the exterior. And another key point is the fact that the network in which the gas flows is a complex real network. Normally, real network, this type of network can be solved using electrical analogies by using the law of Kirchhoff and the Dirac method, for example. But the problem is that taking into account the temperature in this methods is difficult. I tried in my problem itself. and it is not always feasible to add the temperature. So we have to find other methods, and in particular what we will do is to concentrate on a minimal configuration that we will call a thermosyphon. I will describe it later, and then we will add more and more complexity, and we will see how to deal with the study of our general network. So the most common approximation for taking into account also the temperature is the Boussinesq approximation. You can see here that in the Boussinesq approximation we have the density that is that varies slowly around a characteristic density rho c, and it is linear with the temperature. And in this case, the flow is uncompressible because the divergence of velocity is null. But the problem of Boussinesq is that it's valid only for small gamut of temperature. So in some cases, it is not feasible to use this approximation. I show you here some example of the application of Boussinesq. For example, the most classical are the Rayleigh-Bénard flow, in which you have an heated source here and a cooled source here, and the differential heated cavity in which the heated source and the cooled source are at the sides of the cavity. I have introduced Boussinesq. In order, what is more complex than Boussinesq is the Low Mach model, in which the density is no longer linear in temperature and the flow is no more incompressible, since the Low Mach model stays between Boussinesq and compressible Navier-Stokes Mach-wise. So what we have done, we have developed a one-dimensional Low Mach model that is richer than Boussinesq. We have conceived a numerical algorithm that is capable to deal with both discontinuity and periodicity. We'll see that they are the main difficulties of our work. And we have implemented a coupled numerical algorithm and implemented in C++. And we don't forget the optic of the industrial application of this work. And last but not least, we have constructed an analytical solution to validate our algorithms. So we start from the physical and mathematical modeling. In particular, we take the three-dimensional compressible Navier-Stokes equation with boundary conditions, and we want to find some averaged equations thanks to the characteristics of the geometry of the problem. And we do this by making a procedure in which the key points are the thin layer approximation and the averaging on the cross section. This averaging allows to construct a velocity that is no more vectorial, but it is a scalar that is an average of the velocity on the cross section. And this averaging also allows us to introduce the shear stress and the heat flux at the wall that will need some modelization to close the problem. So the averaging equations are the following, in which the variable we want to study are the density rho, the velocity u, the temperature T, and the pressure P. And we consider a law for the gas that is ideal. So starting from the averaged equation, we have constructed the following Low Mach model. In the model we have constructed, you can see that we have that the divergence of velocity is no more zero with respect to Boussinesq, and in particular is function of the thermodynamics of the problem. And we have a decoupling of pressure. We have a dynamic pressure pi and a thermodynamic pressure P. Moreover, we have also an equation for P that derives from the periodic boundary condition. We will see in a few slides how it arises. I remember that the modelization, like I said before, of the heat flux and shear stress at the wall is the following, and in particular we suppose laminar flow. So the shear stress at the wall is linear with the velocity, is not quadratic. So this is our model, and I will show now the key step to find the model starting from the average equations. At first, we can give the dimensionless equations, and from the dimensional equations, we become aware of the fact that the Mach number can give some stability issues in the momentum equations, because if it is small, there are problems of stability in that case. So this justifies the use of a Low Mach model in the case of Mach number that is small. And since that in our problem, in our problem the Mach number in the real application is around 10 to minus 2. We can make an asymptotic approximation in powers of Mach. And if we make this procedure, we find the very important feature of the model, that is the decoupling of the pressure, as I already said, in a dynamic pressure and thermodynamic pressure. And the other key point is the construction of the relations for the divergence of velocity and the pressure P. For the divergence of velocity, you can see that we can make some computations and find it is, as I already said, the function of thermodynamics, and it is small. It is a small quantity. It is no longer zero as in Boussinesq, but it is small. That's the reason we call it a weak compressibility relation. So it is due to the fact that Mach tends to zero. It is not general Mach. And as I already said, for the pressure P, we have that the periodic boundary condition make arise this equation, and so our model is peculiar to closed domains with periodic boundary conditions. If not, we would have another closure equation for P. So that is the model, and we can make a global comparison with Boussinesq. So in Boussinesq, the flow is uncompressible, but we have seen that we have variation of the velocity in space. In Boussinesq, we have a particular form for the density that is linear in temperature, while in our model the relation is not linear. And we have the fact that in Boussinesq there are no variation of pressure. The reference pressure is constant, and while in our model it varies to the periodic boundary conditions. So this is the model. Now let us pass to the analytical solution. The analytical solution is important because we can validate our algorithms. So we made a study foreseeing how we can go far in searching an analytical solution. So we start from the construction of a stationary Low Mach model. This is the general model we constructed. We can make the assumption of stationarity and simplify a bit of terms. And then we added the assumption of neglection of the nonlinear term. And this is the simplified model. And we can add some definitions to write the analytical solution in a more suitable way. So it can be seen in this way, in which we have introduced the flux and I will speak of flux and velocity in exchangeable way. So this is the stationary model. We start from the simpler configuration, and we construct more complex analytical solutions. So this is the analytical solution for an open pipe with an inlet temperature and flux, and an outlet dynamic pressure P out. And these are the analytical solution, and they are well posed, and there is no problem. Given the inlet and outlet quantities, it is well established. And you can see the definition of two quantities that will be important in the future, that are the quantity gamma. This is the ratio between the flux and the temperature, and and lambda, that is an intermediate length. It is bigger than the radius and smaller than the length L, and it will be important in the following. Here we have also the introduction of another parameter that is important. I come here that here we have a stationary pressure P infinity that will be important also in the future to focalize on. So the pressure P from this solution is constant. So starting from this solution, we can go further and take in consideration the configuration I showed you before, the thermosyphon. The thermosyphon is made of 4 pipes. 2 pipes that are vertical, one heated and the other cooled, and 2 adiabatic pipes here, and the flow is due to the gradient of temperature. And you can see here, for example, the solution for the heated pipe and the cooled pipe. I didn't report the analytical solution for the adiabatic, because for the adiabatic temperature and flux are constant. And you can see that the solution is no more well defined, because the inlet of a pipe are the outlet of the other pipe, and vice versa. So the periodic boundary conditions don't allow us to find easily an analytical solution, because we don't know these quantities. And so what we do is to use the laws of continuity and conservation of the flow inside this conservation, and we find a function of lambda equal to 0. This is a nonlinear equation in lambda, and we solve it with a Newton iterative method. So once found lambda, we can find all the unknown of the problem, and so we can find an analytical solution without singularities, without problems. Here I show you the results for the analytical solution for a given TC and TF. and you can see here that the temperature and the velocity are have the same shape. They differ only by a constant. And important here is to remember that the quantity nu here is constant, is an assumption we've made for the analytical solution. On the thermosyphon, it is possible to make a comparison with Boussinesq, in the sense that we have that the function f of lambda that I presented before can be constructed with the same procedure for Boussinesq, and where we have introduced the relative temperature epsilon, and we have proven analytically that the limit of f Mach is f Boussinesq for epsilon that goes to 0. This in the case in which the product G1, it is this non-dimensional parameter, times epsilon is over the order of 1, so that this function is no more function of epsilon. And here I show you the graphically version of this relation, in which you can see that the lambda is a function of G1 for different values of epsilon for the Low Mach model, and you see that it tends to Boussinesq here in purple as epsilon goes to 0. So now that we have studied the thermosyphon, we can go further and study a junction. And here I present you the results for an open junction. Here the unknowns are at the junction, in the sense that for the inlet pipe, for the pipe that enters in the junction, we have that the outlet pressures are unknown because the pressure at the junction. And for the inlet pipe, for the outlet pipes, their inlet temperature and flux are unknown because they are the temperature and flux at the junction. So we have some unknown here, and in particular we have 2m plus n unknown. So we have to find some condition at the junction to close the problem. And the condition at the junction that we have imposed are the continuity of the dynamic pressure at the junction, the continuity of the outlet temperature at the junction, and the law of conservation of mass and energy. We notice here that the law of sum of velocity equal to 0, that is a bit link with Kirchhoff, it derives not from the mass conservation as expected, but derives from the energy conservation. And this is due to the ideal gas law. So if we combine what we have done for the thermosyphon to what we have done for the junction, we can obtain an analytical solution for more complex configuration. For example, here I show you the ladders. So there are some thermosyphons in which we add some pegs to introduce some junction, and we notice that if we take a thermosyphon with only in which we had only few unknowns, we had one peg, we obtained 17 unknowns. If we add some more 2-3 pegs, it arrives to 47. So it increases very, very a lot with the complexity of the configuration, we have found an analytical solution for this configuration, at least to test the analytical solution for the junction, but we have left the analytical solution for more complex, and we know that it can be done, but it is not feasible to do. So at least we have an analytical solution for the thermosyphon, an analytical solution for the ladder to validate all our algorithms. So I will speak now about the numerical algorithm we have constructed. Here we have the full system of equation, and what type of equation we must face. We have a transport equation for the temperature. We have a prediction type equation for the pressure, in which the pressure is a Lagrange multiplier, and this equation can be coupled with the quasi-incompressibility equation by constructing a projection prediction method. And then we have the equation due to the periodicity for P. So how we constructed the numerical algorithm for these equations. Here is the mesh we used. We considered the pi on the nodes and velocity and temperature at the cells. It is not common to put temperature at the cell. I made this for making the laws of the junction easy to apply. Because at the junction we have outlet, we consider the mass and energy conservation law, in which they appear the outlet temperature and outlet and inlet temperature and velocities. That's just a choice. And what algorithms we have coupled? We've used finite differences for the pressure P. We have used the method of characteristics for the temperature. And we have used a splitting algorithm for the dynamic pressure and the velocity. So the splitting algorithm consists in a procedure in which you can see that we have no non-null divergence, and this is different from the classical splitting procedure in which the divergence is considered null. And here is important that the splitting procedure comes after the computation of temperature. And we have seen that knowing the temperature means to know eta, because eta is only function of the thermodynamics. So we can use a splitting procedure in which we know the divergence of velocity. During the procedure, we construct the middle velocity U star, and we find an equation for the pressure. The equation for the pressure we want to solve is not the one of the projection step, but we want to use the information we have. We know eta. So to do this, we make the derivative in space of this equation so that it appears as the derivative of u. And we can find an elliptic equation for the pressure, but we have to pay a price. We find that, as you remember, the sinus theta changes pipe from pipe. So here we have a delta of Dirac that appears. And we have to deal with the presence of delta of Dirac, and it is the main difficulty of the numerical resolution. So in a thermosyphon, we can write the equation for the pressure in this more abstract way, in which we have a regular function f and the Dirac delta that appears. And for a thermosyphon, by using the distributional derivative of the sinus theta, we can find the following coefficient of the deltas. So we can make this computation also for the other configuration. For now, I will concentrate on the thermosyphon because for the other configuration is simply an extension. To solve this type of equation, we use a finite element method, a finite volume method. So here is the classical scheme of the finite volume method, in which we have the definition of the fluxes and the average of the term. What we do is to say, okay, but at the corner of the thermosyphon, you have a pipe that this is vertical and the other that is horizontal, and in that corner, the flux is not continuous. Normally, the flux is supposed to be continuous from one side to the other, but exactly in the corner is not continuous. So we have a law to add that to say that the flow is not continuous, and it is exactly the variation of the flux is exactly the magnitude of the delta. And this new relation allows us to modify the scheme by defining the two new fluxes in which we have the presence of the magnitude of the delta. So this key we use a finite volume scheme in which outside of the corner and the junction, this scheme is the classical finite volume scheme, but there is a correction to make with respect to classical scheme when a delta appears. And this is the final system we find for the thermosyphon. We see that the system, the matrix is tridiagonal, so we can use the Thomas algorithms to have a computational cost of only n and not n cubed. So when we add the junction, what happens to our algorithms? When we add the junction, we had to enforce the mass and energy conservation. So we have to find, we have to give some modification of our algorithms to take into account these conditions. And these modifications are at the level of the method of characteristics, in which we introduce a variable t info that gives the information of the energy conservation. In particular, we have that when two fluxes mix enter the junction and mix, they give the entering fluxes establish an outlet temperature that is the same for all the outlet pipes, and it is a weighted harmonic average of the temperatures of the inlet, where the weights are the velocities. The other conservation equation is enforced in the algorithm for pi. The algorithm for the linear system for pi is the same as before, is tridiagonal, the linear matrix, but at the junction is modified to take into account the fact that there are some inlet and outlet pipes, and here you can see the modification we make to ensure the conservation law. We have seen the numerical algorithms, and we have seen the two complexity to phase, the presence of the Dirac deltas and the presence of junctions. I show you a bit of an idea of the code that we have made. We have constructed a code from scratch, and we have implemented in C++. It was an object-oriented programming in which we have constructed a complex data structure, in which we have constructed a network class, and every one of the configuration we have seen, thermosyphon, the ladder, are the sum from an hereditary point of view of this class. We construct a network, we give a list of pipes, we give a list of junctions, and we say which junction is at the left and which junction is at the right of every pipe. So we construct in this way the network, the oriented network, because we suppose that the flow is in a certain direction, and then the sign of the resulting velocity will say to us what is the real and the effective orientation of the flow. So I will show now the results. We start from the thermosyphon. I show you here the numerical solution for the temperature, and you see that it is superposed to the analytical solution, and you can see here also the results for the dynamic pressure and the velocity. Moreover, we have the thermodynamic pressure. Here is a plot in function of the time. Remember, it is function of only the time, P. And you see that starting from different initial temperatures, we reach always the stationary limit, P infinity, of before. That this is like the analytical solution for P. So here are the errors. They are relative errors computed as in this way, and you see that they are of order 1 as expected, and you can see also that they reach some values that are good, I think. Still for the thermosyphon, we can show what happens. For example, this is one of many of the studies we have made to see what changes if we change parameters. For example, if you have the conductivity that becomes bigger, you have the entrance length that becomes smaller. And here there are some dimensionless number we computed on the numerical results, and you see here that we obtain a Reynolds number that is small, as expected, because we suppose laminar flow, and we have a squared Mach that is 10 to minus 4. That is as expected. We expected that the Mach was 10 to minus 2. And here is interesting that we found that the Freud number squared is of the same order of Mach, and this allows to think to the construction of the model in a different way. This is for the future perspectives. And here I show you the results on this type of showing, because in the following when we will not have analytical solutions, I will use this type of configuration to show the results. You can see that the temperature and the velocity are the colors. And you can see well that the temperature grows in the heated pipe and diminishes in the cooled pipe. So if we want to go for more complex configuration, we start from a three-rung ladder. Here, as I said, we have still analytical solutions, and you can see here the velocity, the temperature, and the dynamic pressure. And you see that also in this case we have a superposition of analytical and numerical solution. And this allows to validate the junction part of the code. And the junction part of the code is also validated by the results I show here. Here I show for every junction the velocity and the ratios between velocity and temperature that show that the sum of this quantity is 0 at every junction. That confirms the conservation of mass and energy. And in a two-dimensional way of seeing, we can understand that in reality, in the symmetric three-rung ladder, the velocity in the middle peg is practically 0, because the symmetricity, the symmetry of the configuration makes that the flow does not want to go in the middle pipe. And if you see, you can notice that the temperature behaves as a thermosyphon. It practically does not go in the middle pipe. And we have in this sense, we have made a study of where to put the rung to make the velocity in the middle rung change. And here you can see L is the ratio between this length and this length. And you can see that by varying L, we have that the velocity is 0 for L equal to 1. And it is negative for L more than 1 and positive for L less than 1. As you can see here, we have that the velocity becomes bigger and bigger in absolute value as the middle rung comes near to the extremes. And for example, you can see also here for the six-rung ladder that the same thing. And here I show how the code can perform on more complex configurations. As I said, the six-rung ladder, and here, for example, I show what results with a four-junction with a junction of order 4. Here you can analyze this type of configurations and see, for example, that in some junction we have continuity. In other junction we have that an inlet temperature of an inlet low temperature, an inlet high temperature here can establish a middle valued temperature here. So analyzing this junction is interesting in these configurations. And you have, for example, here the case in which we have an adiabatic pipe.